Hello everybody. So in this video we're going to solve one more example on the differential analysis of the fluid flow and the analytical solution of the equations of motion and the continuity equation. So here we have a case for a steady, incompressible, parallel laminar flow of a film of Newtonian oil with constant properties falling slowly down an infinite vertical wall. So this is a lot of information here. So what we have is first the assumptions that we have to make, or the conditions that must be satisfied so that we can use Navier-Stokes equation. So it says it's where is it? Newtonian oil with constant properties and incompressible flow. So these are the conditions needed for Navier-Stokes equation. It says it's a steady flow. So the change of time of any change with time is going to be zero, which is this. And it says that it's falling slowly down an infinite vertical wall. So an infinite vertical wall means that one of the dimensions is very, very big, so that it can be considered a two-dimensional flow. So the third dimension has no effect on the velocity profile. And here we see that the two coordinates that we have are x and z. So it means that, and it says, by the way, it says parallel laminar flow, which means that the velocity has only one component, which will be only in the negative z direction. Okay, as we see in the figure. So this is the velocity direction. So the velocity in x and in z and y is zero. And so since we have these two coordinates only here, it means that the third coordinate is the one that we are not considering. So we consider it two dimensions only in x and z, and so any derivative with respect to y would be cancelled. It says that the oil film thickness is h and the gravity acts in the negative z direction, downwards in the figure. So the gravity acts downward, which means that gx and gy is 0 and gz is negative g. And we also know that the velocity is parallel, has one component, so ux and uy are zeros. It says that there is no applied force or pressure driving the flow, so the flow is only due to gravity, which is mentioned here. The oil flow falls by gravity alone, and we need to calculate the velocity fields in the oil film and the velocity profile. It says we are going to neglect the hydrostatic pressure of the surrounding air, meaning that the pressure around is all atmospheric pressure. So since there is no pressure applied, we can consider that the pressure everywhere is zero. Keep in mind that this is a film that's open to the atmosphere, so the effect of hydrostatic pressure cannot be considered as like the previous case where we had the fluid confined between two plates. Here it's open to the atmosphere. So the pressure can be considered the same everywhere. We can consider the change of pressure with x is the same as y, as in z is 0. So these are the assumptions that we can make here for the boundary conditions. We have one side of the fluid which is sticking to this fixed wall. So this is fixed wall, it's not moving, so the velocity here is 0. So at x equals 0, uz is equal to 0. And for this surface, it's an interface between oil and air, and this is what we called before a free surface. And at this free surface, the shear stress is going to be 0. Or since it's Newtonian fluid, shear stress is mu times duz by dx. So we can put duz by dx is 0 at x equals h. So these are all the assumptions that we have. So we can move to the next step, which is simplifying the differential equations. We are going to start with the continuity equation. The velocity in x and the velocity of y is 0, so we have only velocity in z. And again, we said this last time, this doesn't mean that the velocity is constant. It means that there is no dependence for the velocity on z, which we know that there is no effect of temperature on the time on the velocity. There is no effect of y, and now we know there is no effect of z, so there is only effect of x, which means that uz is only function of x. For the component of Navier-Stokes equation, the x component, ux is 0, so all these terms are zeros. We said that the dp by dx is 0, there is no gravity in x direction, and these three are zeros, so the equation is not helpful. The same for y equation. If you try this for the y component, you will get the same output, so I'm not going to do this. You can check it yourself. The last equation that we have is the z component. We know that there is no change with time. Ux is 0, uy is 0, duz by dz is 0. We have dp by dz is 0 as well, and then we have gz has a value, and then uz is function of x, so this is not 0, and uz is not function of y and is not function of z. So the equation reduces to the second derivative uz with respect to x is negative rho gz over mu, and gz, as we said, is negative g. Okay, so this is going to be positive rho g over mu. Anyway, so this is the equation that we have, so we can integrate it twice, and then we find the uz as we see, it's second order polynomial in x. And given these boundary conditions, we can substitute to get the value of or the formula for C1 and C2. So for C2, if we apply the first boundary condition, uz is 0 when x is 0, so this is 0, 0, and 0, so C2 is going to be 0. For the second boundary condition, we'll get the derivative, which is rho g over mu times x plus C1. It's equal to 0 at x equals h, so we will substitute with 0 and x equals h, and from this we can get a formula for C1, and by substituting here we can get with C1 here and C2 here, we can get the shape of uz, which is rho gx over mu times x over 2 minus h. So this is what we need to get from the requirements of the equation. Just one thing, which is to verify the results, which is something we can do, is to draw the profiles. So I drew two sets of profiles here. The first, I'm keeping the density constant and I'm changing the viscosity, and the second, I'm keeping the viscosity constant and I'm changing the density. I picked the thickness 5 millimeters, and I'm calculating the velocity over the whole range from x equals 0 to x equals 5 millimeter. And this is what we see here. You can see that and it makes a lot of sense. The first is if the viscosity is low, which is this is the minimum viscosity, you will have high velocity of flow, while as we increase the viscosity, the velocity keeps decreasing. Okay, and this is expected. If you think of this as let's say oil and water, or honey and water, of course the honey will flow at very, very much slower rate or speed than water, and this is what we see here. And this makes sense from the equation as well. If you look at the equation, the uz is inversely proportional to the viscosity. Okay, so this is one thing. In the second plot, you'd see here that it's the same thing. Everything is the same except I'm changing the density. And as we increase the density, so it's here 600, 800, 1000, 1200 kilogram per meter cube. And as we increase the density, as the velocity increases, and this makes sense as well, because as you increase the density, it means that the gravitational force is stronger, and this pulls the liquid downward at higher rate. And it also makes sense from the equation because this density is directly proportional to uz. The last thing is that for all of the data sets that we make, or the profiles that we drew, the velocity is always 0 here, which agrees with the boundary condition. The second is you see that the slope will all be 0 here. Yeah, the line is almost the tangent would be horizontal here, which agrees with the boundary condition that we made as well. So these plots give us some feeling of the parameters, how they affect the system, and make sure that the equation that we got makes sense. So I'm going to stop here. Inshallah, next time we're going to go through one last example. So I'll see you then, inshallah. Goodbye.